Alright, so this is going to be part 3 of integral problems with polar. Now you can see here, this problem is asking us to find the area between two curves, okay? And we haven't done that yet with polar, but we've done that with other functions. That was the beginning of Calculus 2, actually. Okay, that was one of the first things that we did. So here's kind of what we're talking about. We're talking about, we have our bounds from A to B, right? And we have two functions, okay? So if we want to find the area in between, right, this area in here, what we have to do is subtract the area under g of theta from the area under f of theta, okay? And that ends up getting us our area in between curves, right? So how we do that, right? We have the area equals 1/2 the integral from a to b of this, right? Of our, remember we have to square it, so we get f of theta squared d theta minus 1/2 the integral from a to b of g of theta squared. And here's what I recommend you do, is just put these together, and f of theta squared minus g of theta squared d theta. All right, that's probably going to be a little easier, a little less work. Okay, so with this, we can now solve our problem. So the first thing that we're going to have to do for this problem is figure out what r equals 4 sine theta looks like, okay? We can all understand what r equals 2 looks like, but 4 sine theta, let's make sure we're all on the same page here. We view r and theta as Cartesian coordinates, okay? So we're going to have, okay, 4 sine theta, that looks like this, okay? That's one little period of the wave. Now, this has its max at 4, its min at -4, and it's going to achieve that max at pi over 2. We get pi, 3 pi over 2, and 2 pi. Okay, this should all seem familiar, so I'm kind of going through it a little quicker. Now, if we actually graph this, we have our polar axis here. This is going to look like just a circle. Let's see if I can just draw this circle without being terrible. Okay, that's not the worst thing in the world, I guess. And this is going to be at a height of 4, so it's going to be a circle of radius 2, but it's going to be on top of the polar axis, as you can see. R equals 2, well, that's just going to start at, let's say r equals 2 is right here. Let's move it out, because actually it's got to be even with that. So now we have something here. Okay, so now we have our two circles, and it's outside r equals 2 and inside r equals 4 sine theta. So the region that we're talking about is actually this region right here. Okay, so we can see that our top function is going to be r equals 4 sine theta, and our bottom function is going to be r equals 2. Okay, so all we have left to find before we can actually do our integral is we need to figure out what our endpoints are. Okay, remember these are theta endpoints, so we're going to have to figure these out. All we have to do for that is just figure out where 4 sine theta equals 2. For what theta values, right? And of course, you do a little bit of algebra here. We get sine theta equals 1/2. And those two theta values that are relevant here, this is going to be pi over 6 and 5 pi over 6. Okay, now with that knowledge, we can set up our integral. So we're going to get the integral, 1/2 actually, we can pull out that 1/2 already. 1/2 the integral from pi over 6 to 5 pi over 6 of, now we have our, remember our top function, that is 4 sine theta, so we're going to square that, right? We square that to get 16 sine squared theta. And then we're going to subtract our g of theta, right? Our bottom function, which is 2, right? And we square that, so that's 4. And we get d theta. We can take out a 4 here, okay? And we take out a 4, we get a 2 outside. So that's 2, the integral from pi over 6 to 5 pi over 6 of 4 times, well, we can use that half angle identity already to simplify down sine squared. That will become 1 minus cosine squared of theta over 2 we can subtract 1 d theta. Remember, we took out that 4. Okay, so we can simplify this. We get 2 the integral pi over 6 to 5 pi over 6 of, this is now 2, minus this will be a 2 cosine squared theta, or 2 I messed up there. That is going to be 2, you guys are probably like, oh my god, he's a loser, you messed up. Cosine of 2 theta, that's what that is. Yeah. Alright, and this is going to be minus 2 cosine of 2 theta. And we have a minus 1 here. That means that this will become just a, well, this will become a 1 minus 2 cosine of 2 theta. We have our d theta on the end. Let's integrate to the integral, well, nope, we're integrating here. So we get 2 times theta minus, this will now become just a sine of 2 theta, evaluated from pi over 6 to 5 pi over 6. God dang, train. Stupid. Okay, now we do our evaluation step here. We get 2 times 5 pi over 6 minus sine of, well, this will now be, it's 2 times that, so we get 5 pi over 3. Okay, and we'll also get, I can also throw this under here, we're going to get minus theta, which is going to be pi over 6, and it'll be minus, so plus, be sine of pi over 3. Alright, and just doing this out here, we're going to get 2 times 5 pi over 6 minus pi over 6, that's 4 pi over 6. We can simplify that to 2 pi over 3. And we get, well, we have a minus sine of 5 pi over 3 plus sine of pi over 3. Sine of 5 pi over 3, that's sine of 300, which is also sine of 60, but remember, it's going to be negative, so this actually will become a positive, all right? And that will be just rad 3 over 2. And of course here we're going to get another rad 3 over 2. And we already took care of this negative pi over 6. So we're going to get a rad 3 here. So all we will actually end up getting is 4 pi over 3 plus, so it'll just be a 2 rad 3. All right, and that's our answer. So a little more challenging, I guess, when you have area between curves rather than the area under one curve, but again, it is doable, okay? So that's gonna do it for this video. So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for parametric and polar, the explanation video for integrals with polar, and the next video in the series. See you soon.